Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Today we will continue our discussion on our course, GTD course, Generation, Transmission and Distribution course on chapter 5. So today in chapter 5 we will focus on constant of transmission line and we're focusing on electrical characteristics. So basically the content of these topics will cover introduction, resistance of transmission line, inductance, and also capacitance in the transmission line. As an introduction, the transmission line has 4 parameters that usually being calculated and analyzed. First is resistance. Resistance causes power loss in the conductor due to their I/R losses. And second, inductance that affect the power transmission capacity. Third is the capacitance that causes a charging current to flow in the line. And fourth is the shunt conductance that caused by a leakage current and it is very small, so it can be negligible. So we will not discuss further on the shunt conductance in this topic. These parameters determine whether the efficiency and voltage regulation of the line will be good or poor condition. And these parameters are uniformly distributed throughout the line and are represented as lump for the purpose of analysis. So let us look at the resistance of a transmission line. Basically, as I mentioned before, resistance is the most important causes of power transmission or power loss in transmission line due to their I/R loss. For the resistance R of a line conductor having resistivity ρ, length L, and area of cross-section A can be represented in terms of R equal to ρL divided with A. Suppose that you have a conductor line like this. So you have a length of conductor line such as this one, and then the cross-section area is here, cross-section area, and then the resistivity ρ is determined by the type of material used for conductor. So the variation of resistance of metallic conductor versus temperature is increased with increase in the temperature. So the formula for the resistance at different temperature is R2 equal to R1, 1 plus alpha T2 minus T1, where R2 is the resistance at temperature 1, R1 is the resistance at temperature T1, while alpha is the temperature coefficient at reference temperature. So this table shows resistivity and temperature coefficient of conductor material at T equal to 20 degrees Celsius at different material for various material from iron, steel, platinum, molybdenum, tungsten, zinc, and nickel iron. So you can see here there are different temperature coefficient of resistance. Most of them are to the 10 to the power of -3 per degree Celsius. And also you can see the various electrical resistance for different material from iron until to the nickel iron. So let's see the skin effect. Skin effect for direct current. Okay, before that, we will see the direct. In the case of direct current, current is uniformly distributed over the whole X section of the conductor. Let's say this is the conductor, so the current will flow at the whole section. The whole section, there is a current flow throughout the conductor. Okay. But for the case of alternating current, AC, current does not distribute uniformly. Current distributes near the surface of the conductor. It has tendency to concentrate near the surface of the conductor because of the characteristic of current that is alternate. Okay, so more current are focusing on the surface of the conductor, and The tendency of alternating current to concentrate near the surface of a conductor is known as the skin effect. From this figure, you can see that this is the example of the cross-section of the conductor. So for the alternating current case, current flows over the surface while no current flow in the middle. So this is what we call the skin effect. So due to skin effect, the effective area of X-section of the conductor through which current flows is reduced. So let's say this is the conductor, and then most of the current are flow at the surface of the conductor. So effective area here, A effective is reduced. A effective is reduced when compared to the DC current in DC conductor. So the conductor resistance is slightly increasing. Reducing the effective area will increase the resistance. So when resistance is increased, so then the copper loss, that is I square R, also increase. The skin effect depends upon the following factors: that is nature of the material, diameter of the wire, of course the size of wire. Increasing diameter will increase the skin effect. Frequency, that is increase in frequency will increase also in the skin effect. Finally, the shape of wire. Okay, skin effect is less for standard conductor than a solid conductor. Okay, let's say if you have a conductor like this, okay, combination of conductor stranded in a bundle form like this, when compared to solid conductor like this, so skin effect is less in this type of conductor when compared to the solid single piece conductor. And the skin effect is negligible when the supply frequency is less than 50 Hz and conductor diameter is small, that is more than 1 cm, less than 1 cm. Okay. Now we look at the case of inductance of a transmission line. The inductance of a circuit is defined as the flux linkage per unit current according to the basic right hand grip rule. Okay, so if you use your right hand, okay, and you grip it, so the current flow is like this, like your remaining finger is the current flow, and then the flux generated is your thumb finger. Okay, this is a thumb finger. So current flow like this, so the flux will be generated at this thumb. This is right hand grip rules. So there are two important cases of flux linkage. That is flux linkage due to a single current conductor, and also flux linkage in parallel current carrying conductor. So let's say the case of a single current conductor, that is this figure. So only one conductor is used. So when current flow, so flux linkage generated around the surface of the cross-section of the conductor. Similarly, from this figure we can see that the flux flow surrounding the near to the surface of the conductor, while there is no flux flow in the middle of the conductor due to the cause of the skin effect. The flux also has a different flux based on the distance of the radius and also the flux linkage surrounding the conductor. In the case of a parallel current carrying conductor, so the flux linkage also, the inductance also will be generated between two conductors. For example, between conductor A and conductor B, there is a distance D1. So inductance will be generated in this conductor. Between A and C, there is D2. So inductance 2 will be generated. Similarly, between A and D, inductance L5 will be generated. A and E, A and F, and so on. So let's see, consider a radius of conductor A and B as R1 and R2 respectively. So radius of conductor A is R1 and radius of conductor B is R2 in this case. So there is a distance between A and B that we call D. So let's say the total inductance of conductor A. In conductor A, the total inductance in A is 2 times 10 to the power of minus 7 times 1 over 4 plus log exponent D over R. Or we can simplify this equation to become LA equal to 2 times 10 to the power of minus 7 log exponent D over R prime, where R prime is 0.77R88 R. Okay, we will see how we got this value later. So from the equation to calculate the inductance, basically the equation of inductance is 10 to the minus 7, 10 to the power of minus 7 times 1 over 2 half plus 2 log exponent D over R. This is for two-wire line. So this inductance is happen in conductor A, for example, and then we can simply take out 2 from this equation. So if we multiply this equation with 2 over 2, okay, 2 over 2. So this equation with 2 over 2, okay, and we take out these 2. So we got 2 times 10 to the power of minus 7, 1 over 4. 2 here already we move here. So we got 1 over 4 plus log E D over R. So further 1 over 4, if we convert into log exponent, we can simply convert it as log exponent 1 over 4. So from this you can simplify further the equation, that is log E D R exponent minus 1 over 4. Okay. So if we put R exponent minus 1 over 4 as R prime, so then we got the equation of inductance in conductor A as a 2 times 10 to the power of minus 7 log exponent D over R prime Henry per meter, where R prime is R exponent minus 1 over 4, which is 0.7788 R. So this is how we got the value of R prime. And R prime is called geometric mean radius of the wire. Okay, now let's say the total inductance of conductor A that we discussed previously is LA equal to 2 times 10 to the power of minus 7 times 1 over 4 plus log exponent D over R. Previous equation. So for similar conductor diameter, okay, LA equal to LB. Okay, if we have 2 conductor diameter, that is LA. Let's say this conductor has a similar diameter A and B. So B also have the same equation as inductance in A. Okay. So the total inductance per loop inductance is nothing but LA plus LB equal to L. So equal to 4 times 10 to the power of minus 7 times 1 over 4 plus log exponent D over R Henry per meter. Let's see the example 5.1. A single phase system has 2 parallel conductors with 2 meters apart. Single phase system has 2 parallel conductors, let's say conductor A and conductor B, which is 2 meters apart in the distance. Okay. The diameter of each conductor is 1.2 cm. Diameter is 1.2 cm. Okay, diameter, let's say diameter 1.2 cm. Calculate the loop inductance per kilometer of the line. So here given D or distance equal to 2 meter, distance between two conductor. So from the diameter given, we can calculate the radius, which is radius equal to 1.2 cm divided with 2 radius. So equal to 0.06 meter. Now loop inductance per meter length is nothing but L equal to 4 times 10 to the power of minus 7 times 1 over 4 plus log exponent d over r Henry per meter. So we just use this value, d convert here to meter, and then r is 0.06 m meter. So we got the value of 24.23 times 10 to the power of minus 7 Henry per meter. So we can convert to kilometer. So we got 24.23 times 10 to the power of minus 4 Henry per kilometer. Or we can use it as 2.423 millihenry per kilometer. So this is the loop inductance per kilometer of the line. Now we see the inductance of three-phase overhead line. So consider three conductors, that is A, B, C, of the three-phase line carrying IA, IB, and IC respectively. So let's say this conductor A carry a current IA, and then there is conductor B also carry a current IB, and conductor C also carry a current IC. Okay. And let D1, D2, and D3 be the spacing between the conductor. So D1 space between B and C, D2 is the space or distance between A and C, while D3 is the space or distance between A and B. So for the case of three-phase overhead line, there are two cases that we can discuss. First is symmetrical spacing. The meaning of symmetrical spacing is that all distance are same. All distance between three conductors are same. Between A and B, here in A and B is D, distance is D, A and C also D, B and C also D, distance are same. So if the conductor A, B, and C are placed symmetrically at the corners of an equilateral triangle of side D, then D1, D2, and D3 equal to D. Okay. So the inductance of conductor A, B, and C will be same. That is LB equal to LC equal to LA equal to this equation. This is for the case of symmetrical spacing. Let's see what happens if spacing are unsymmetrical, like the case of this figure. So we have three conductors, A, conductor B, conductor C. Okay, 1, 2, 3. So the spacing between A and B is D3. B and C is D1. A and 3 is D2. So the spacing is unsymmetrical. The distance also not in the same. So in the case of three-phase line conductor are not equidistant from each other. So the flood linkage and inductance at each phase also differs. So this results in unequal voltage drop in the three phase. So to calculate this, we can use a transposition method. That is to interchange the position of another conductor over an equal distance. So we will make the distance as an equal or average distance between these three conductors. So at the end, each conductor will have the same average inductance. Okay. So for the case of unsymmetrical spacing, the formula to calculate the conductor A, okay, LA equal to 2 times 10 to the power of minus 7 times 1 over 4 plus log exponent square root 3 of D1, D2, D3. Okay, D1, D2, D3 is nothing but the space between the conductor itself. Let's say D1 is the space or distance between AB, D2 between BC, and D3 between AC. R is the radius. Assume that the radius are constant or similar for conductor A, conductor B, and conductor C. Similarly, for conductor B, the equation is similar as conductor A, and inductance of conductor C, LC, also similar as conductor B and conductor A, provided that we use this equivalent spacing at the equation. Okay, and D or distance equal to square root 3 D1, D2, D3 is known as equivalent spacing for unsymmetrical transpose line. Now we look at the concept of self-GMD and mutual GMD. Okay, GMD is geometrical mean distance. Okay, it simplifies the inductance calculation that related to multi-conductor arrangement. Okay, there are two GMD, that is self-GMD, DS. Okay, DS depend on size and shape of the conductor. Okay, size and shape, DS. So for solid round conductor with radius R, so DS will be 0.7788 R. Okay, 88 R. Like this. So the inductance will be 2 times 10 to the power minus 7 times 1 over 4 plus log exponent dr, or we can change this R to ds, that is self geometrical mean distance, ds. ds value is 0.7788 times R. Second is mutual GMD, mutual geometrical mean distance, that depends on the spacing. Spacing is nothing but distance from one conductor to the other, and it is independent of the size, shape, and rotation of the conductor. So there is some formula for inductance in terms of geometrical mean distance. Okay, geometrical mean distance GMD. So for single phase line, the inductance per conductor per meter will be 2 times 10 to the power of 7 log exponent dm over ds, where ds is 0.7788 R and dm is spacing between conductor, or D, okay, for single phase line. While for the case of single circuit 3-phase line, okay, single circuit 3-phase line, so inductance per phase per meter is equal to 2 times 10 to the power of 7 log exponent dm over ds, where ds is similar for the case of single phase line, that is 0.7788 times radius r, while dm is square root 3 of d1 and d2 times d3, as we discussed previously. While for the double circuit 3-phase line, the inductance per phase per meter is 2 times 10 to the power of 7 log E dm over ds, where ds is ds1 times ds2 times ds3 square root 3. dm is the distance between DAB, DBC, and DCA with power of square root 3. Let's see example 5.2. For the inductance per kilometer, find the inductance per kilometer of the line for conductor radius of cm. Okay, this is the three-phase conductor. We have three conductor, 1, conductor 2, and conductor 3 with distance D12 2 meter, okay, D23 2.5 meter, and D13 4.5 meter. So to find the inductance, we can use this equation. So because of the distance is not similar, it's not the same, so we can use the equilateral spacing formula DEQ, that is D12 times D23 times D31 square root of 3. So we just convert the value, and then we will find that the distance equivalent distance is 282 cm or 2.82 meter. So to calculate inductance per phase per meter, okay, you can use the formula that is 10 to the power of minus 7 times 0.5 plus 2 log exponent the equivalent divided with the radius r. So the equivalent is from this one, okay, and r is the radius given is 0.62. So we got 12.74 times 10 to the power of minus 7 Henry. Or we can convert to millihenry. We got 1.274 times 10 minus 3 Henry, or 1.274 millihenry. So this is the inductance per phase per kilometer of the line conductor. Now let's look at the case, different case of different distance of conductor. So calculate the inductance of each conductor where the diameter is 2.5 cm. Okay, so you have conductor 1, conductor 2, and conductor 3, where the distance is 2 meter between conductor 1 and conductor 2, 2 meter also between conductor 2 and conductor 3, and 4 meter between conductor 1 and conductor 3. So because the diameter given is 2.5, so we can calculate the radius of conductor 2.5 divided with 2, so we got 1.25 centimeter. That is conductor radius. So we can use also this formula to calculate the inductance. So basically we calculate the equilateral spacing, equivalent equilateral spacing, that is EQ. So we just convert the value of D12, okay, D23 and D31. So we got 2.52 meter, that is 252 centimeter. Then we convert the value to the equation. So we got 252 and 1.25 is the radius. And finally we got 11.1 times 10 to the power of 7 Henry, or 1.11 millihenry. That is the inductance per phase per kilometer. Okay, now let's look at the capacity of a transmission line. So basically, we will look at the electric field and potential difference at the beginning. So transmission line conductor exhibit capacitance with respect to each other due to the potential difference between them. Okay, let's say this is a conductor. So there will be a capacitance between the conductor due to potential difference. The amount of capacitance between conductor is a function of conductor size, spacing, and height above the ground, while the capacitance C is the ratio of charge Q to the voltage V. Okay, this formula to calculate the capacitance Q divided with V. Q is the charge, V is the electric potential. Now let's see potential at a single conductor. Okay, only one conductor. So consider conductor A with radius R. Okay, conductor A with radius R. The conductor operates at a potential VA with charge QA coulombs per meter. Okay, VA with potential of QA coulomb per meter, and the electric intensity E at a distance x. See this distance x from the center of the conductor, here, center, is E equal to QA divided with 2 pi epsilon naught. Epsilon naught is the permittivity of free space or permeability of air, where epsilon naught equal to 1 over mu naught C square. Mu naught is the permeability of free space, C is the speed of light. Okay, as the x approaches infinity, when x is increased, approaches infinite value, so the value of E approach 0. Okay, the potential difference VA between conductor A and neutral infinity or infinite distance is given by VA equal to this equation. Okay, QA over 2 pi x epsilon naught dx equal to QA over 2 pi epsilon naught from R to infinity dx over x. So this is the equation of potential difference for conductor A. Let's see the capacitance of two wires. Okay. Consider one phase line. Okay. Consider single phase line with two parallel conductors, each having radius R, separated by a distance d. Okay. We have a conductor A and we have conductor B here. Both have the same R, let's say. Okay. And then with a distance d. So we can calculate the potential difference at VA and VB between conductor A and B to neutral infinite distance as this equation. So this is a very long equation. So the final equation of VA will be this one. Okay. D is the distance, R is the resistance, so R is the radius, Q is the charge capacitor coulomb, 2 pi epsilon naught. Epsilon naught is the permittivity of air of free space. So this is the potential difference at conductor A, while for conductor B, because the charge is negative, so we got negative Q, 2 pi epsilon naught log exponent B over R for the potential difference at conductor B. Right? Okay, both this potential or VA and VB are with respect to the same neutral point. So they will be same neutral point. Since the alike charge attract each other, so the potential difference between the conductor V and B, so between V and between VA, the voltage between A and B, or the potential difference between this to this, okay, will be VAB equal to 2VA. It is 2Q over 2 pi epsilon naught log E d over R. So from here we can see, we can calculate the capacitance, that is CAB equal to Q divided with VAB, Q divided with VAB. So VAB is this equation, VAB. Okay, so simply we can remove this Q and remove this 2. So we got CAB equal to pi epsilon naught divided with log exponent D over R. So CAB is the capacitance between these two wires. So please be reminded that to calculate CAB, first you need to calculate the potential difference at point A and potential difference at point B. So you will get VAB. Okay. Once you got VAB, then you can calculate CAB. Okay, capacitance between wire A and wire B is on this formula. Okay. In some cases, there is for the case of two wire, there is a conductor who connected to the neutral point. So this is the example of the two conductor A and B that is connected to the neutral point here. And from the figure, the line to line capacitance can be considered to be composed of two capacitors in series. So we have this capacitor that is CAN between conductor A and neutral, and we got CBN, which is the capacitance between B and neutral. Okay, so the voltage between the lines divided equally, and the point N is at ground potential. Okay, so capacitance of each line to neutral is twice the line capacitance, which is that capacitance at neutral point, okay, equal to CAN equal to CBN, okay, equal to CAB. Okay, so if we convert, we got capacitance to neutral, which is 2 pi epsilon naught log exponent D over R per meter. Okay, now let's say example 5.4. Single phase conductor is 10 km long line. Okay, the diameter of each conductor is 1.213 centimeter and the spacing is 1.25 meter. Find the capacitance between the conductor and find the capacitance of each conductor to neutral. Okay, to find the capacitance between the conductor, you can calculate using the formula of this. CAB equal to pi epsilon naught log exponent D over R farad per meter. So you just replace the value of epsilon naught, the permittivity of air, D is the distance. Okay, that is 1.213. Sorry, 1.25. The distance is 1.25, and resistance, radius is 1.213 divided by 2. So 1.25 is the conductor spacing. 1.213 times 0.5 or divided by 2 equal to the radius. So we got CAB equal to 5.219 times 10 to the power of minus 3 microfarad per kilometer. Or because of the transmission line is 10 km long, so we can multiply with 10 km. So we got 0.05 to 1 microfarad for the case of conductor with 10 km long. And to calculate the capacitance of each conductor to neutral, we can use this formula. Okay, simply multiply with 2. Okay. Capacitance to neutral is 2 capacitance of AB. So we got 0.1042 microfarad. Again, example 5.5, let a single phase transmission line has two parallel conductors 3 meters apart. Okay, two parallel conductors 3 meters apart. Radius of each conductor is 1 centimeter. Calculate the capacitance of the line per kilometer. Given that epsilon naught as 8.854 times 10 to the power of minus 12 farad per meter. So as solution, we have the radius 1 centimeter. Okay. Spacing of conductor, we have D equal to 3 meter or 300 centimeter. So to calculate the capacitance of the line, we can use the formula. Okay, let's say line AB or BC or line whatever. Okay, let's say BC. So we got CBC. Okay. So we convert this from value. Okay, distance is 300 and R is the radius 1. Okay, over here. So 300 and radius 1. So we got the capacitance of the line CBC, for example, is 0.4875 and 10 to the power of minus 2 microfarad per kilometer. Now we look at the case of capacitance of three-phase line. Similar as inductance, there are two cases. That is one, symmetrical spacing, and second will be the unsymmetrical spacing. Let's say for symmetrical spacing, the distance is D for the three conductors. Okay, between A and B, distance is D, BC distance is D, and AC is also D. So potential difference between conductor A and neutral, that is VA, can be calculated as this equation. This is the potential difference at conductor A to neutral. So this equation that we discussed previously, we can use to calculate the potential of conductor A. So we can calculate also the capacitance A 2 pi epsilon naught divided with log A dr. And this equation is identical to capacitance to neutral for two-wire line. Okay. Another equation that we can discuss for case of symmetrical spacing is that charging current per phase, that is IC equal to B phase divided with XC. Okay, B phase is the phase voltage, XC is the capacitor impedance. Okay. And for the case of unsymmetrical spacing, okay, the capacitance can be calculated as D1, this equation. Okay, CA equal to QA divided with VA, where is equal to 2 pi epsilon naught divided with log exponent D1, D2, D3 square root 3. This is the equivalent distance, okay, of between the unsymmetrical spacing. Alright. Now look at the example 5.6. Three-phase 50 Hz 132 kilovolt overhead line has conductors placed in a horizontal plane 4 meters apart. Okay, distance between A and B is 4 meters. Between B and C is 4 meters. So between A and C will be 8 meters. Conductor diameter is 2 centimeters, so radius will be 1. So if the length is 100 kilometers, calculate the charging current per phase. So basically given B1, that is AB equal to 4 meters, B2 that is BC equal to 4 meters, and D3 that is AC equal to 8 meters. So the equivalent distance, average distance, d1, d2, d3, square root 3. So we got 5.04 meter. Okay. And capacitance of each conductor to neutral. Okay. We can calculate using this equation, 2 pi epsilon naught log E dEq over R. So D equivalent is 5.04, R is 1, because diameter is 2, so radius is 1. So we use this equation and we replace the value in this equation. So we got capacitance per phase, or capacitance of each conductor to neutral is 0.00885 times 10 to the power of minus 6 farad per kilometer. Okay, basically we can just change this to microfarad if we remove this one. While the capacitance per phase for 100 kilometer line, okay, given 100 kilometer line here, is Cn equal to this value times 100, so equal to 0.885 times 10 to the power of minus 6 farad, or simply 0.885 microfarad. So given the line voltage, so we can calculate the phase voltage, which is line voltage divided with square root of 3. So line voltage is 132 kilowatt. Square root divided with square 3, we got phase voltage is 7620 watt. So from the previous equation, we can calculate the charging current per phase, IC. IC is nothing but this equation, V phase divided with XC, that is the capacitor impedance. So V phase is 76210. Okay, XC equal to omega Cn. So we got omega is 2 pi f. So 2 pi f, f is 50 hertz frequency. Okay, and the capacitance for 100 kilometer line is 0.885 microfarad. Okay, this is the phase voltage 76210. So we got 21.18 ampere charging current.